Good morning. This week we have isomerism, GOC, and acidity basicity in our phase 2 or revision syllabus. First 2 days we'll invest on isomerism, then it is GOC, and then we'll study acidity and basicity. So first let's start isomerism. Isomerism, if you see, usually comes under multi-correct or integer questions. So we need to be very specific and very clear about the concept and the count of number of stereoisomers, number of total isomers, number of specifically mentioned structural isomers asked in the question about a particular formula. For that, let us start our work today and revise what all is there to be covered in isomerism. Today's topic is structural and geometrical isomerism. First of all, what is this term isomerism is? Well, molecules having same type of atoms, same number of atoms, hence having same molecular formula, but different physical and chemical properties are called isomers of each other. Are called isomers of each other, and the phenomenon is known as isomerism. Such two molecules which have same molecular formula but different physical and chemical properties are called isomers of each other. Okay, this particular phenomena is seen in history of science from somewhere around 1830 to 1840. In some books it is said 1838, in some it is 1835. So I am giving you a range somewhere in 1830 to 1840. This particular concept have been introduced in world of chemistry. So, what was the origin or what was the root of this word isomerism? This word has been originated from Greek language. Now, in Greek language, it was isos plus meros. Okay, the isomerism has the word has originated from Greek language. It was having a origin of isos plus meros. The meaning of these two is isos is equal, meros is parts. So two molecules or more than two molecules having equal parts were named as isomers way back then. Okay, coming to the classification. Today isomers are of what types and what we study. So in present context, isomers are divided broadly into two. First is the constitutional isomers, which are also known as structural isomers. Second is the stereoisomers, that is the isomerism, which is generated due to different arrangement of atoms with respect to space, with respect to 3D geometry. They are called stereoisomers. Coming back to constitutional or structural isomers, they are of five types. If you see, there are five types of structural isomers. First is chain, second is functional, third is positional, fourth is metamer, fifth is tautomers. Okay, if you go to stereoisomers, they are divided into two categories. One is conformational isomers, second is configurational isomers. Conformational isomers or conformers are rotamers. They are also called rotamers. And the configurational isomers are further divided into two. One is geometrical and second into optical. Okay, this is a very technical distribution, geometrical and optical. I have a personal choice that we can, for our own comfort, should divide configurational into two. One is enantiomers, that is those which are not the mirror superimposable mirror images of each other. And second, we should put diastereomers. Diastereomers are those which are non mirror images of each other. Okay, so I prefer this type of classification, but of course, the technical is geometrical and optical. Because if you do it this way, optically active optical comes into this, and rest all GI and other types of optical comes into the category of diastereomers. So we'll see it further what all this is. Let's first start with structural isomers. A very specific comment on structural isomers these days are not being asked as such, but we should be aware of what it is. So, first out of five is chain isomers. Chain isomers, how to find whether the compound is having chain isomerism, pair of compound is having chain isomerism or not. Always, as a rule, first of all, assign IUPAC name to the structures presented to you in the question. Okay, once you assign the IUPAC name, you will immediately come to know whether the two molecules given, whether the set of molecules given in the question are having same functional group or not. That is step number one. Assign the IUPAC name and check the functional group in the given molecule should be same. Okay. Second, when you'll assign the name, say for example here, this is ethyl benzene. This is 1, 2 dimethyl benzene. So once you assign the name, then you check that is there any change in the root word of substituent or the parent chain. There should be change either in root word of substituent or should be change in the root word of side chain. So this is ethyl benzene, root word remaining benzene and benzene in both. But ethyl is changed to dimethyl, so they are chain isomers. Same case, please practice this by yourself. Ethyl benzene, ethyl pentane, dimethyl pentane. Okay, so they are same. They are same with reference to both are similar examples. Both have similar behavior that they are chain isomers. If I take N-butane versus 2-methylpropane, if I take N-butane versus 2-methylpropane, then these are, when you'll assign name, this is butane, this is propane, so they are also chain isomers. So for chain isomers, we have to give IUPAC name, check the functional groups are same. Okay, then the next step is there a difference in the root word of the side chain or the parent molecule, parent chain in the two? Then they are chain isomers. Next, we move to functional isomerism. So, what is functional isomerism? I would say this is the easiest to identify in a given set of molecules. Again, the step one is give IUPAC name. Because as soon as you'll give IUPAC name, you immediately come to know whether the functional group is identical or is different in the two molecules. Here, when you'll assign IUPAC name, this will end with all. This will have a suffix all, whereas here there is no suffix. This is an alcohol, this is an ether. They exhibit functional isomerism. Now, this otherwise you may find to be identical, that both are a carbonyl functional group. But no, if you go by IUPAC name, you will see that the suffix in the two is different. See, here you will call propanal, and here you will call propanone. So one is having al, other is having on. So different functional group. One is aldehyde, another is ketone. Aldehyde and ketones are functional isomers of each other. Okay. Moving to point number third. Here OH is attached to sp3 carbon. And here is OH is attached to sp2 carbon. Here the functional group is alcohol. Here the functional group will be called phenol. So remember that alcohols and phenols, if they share the same molecular formula, are functional isomers of each other. Alcohols and phenols are functional isomers of each other. Okay, let us move to point number 4, different degrees of amines. Say CH3, CH2NH2, CH3NHCH3. Formula is same, but one is a primary amine, another is a secondary amine. So if there is different degrees of amines, they are called functional isomers. Ring chain isomerism, example number 5 is ring chain isomerism. When one of the isomer is a ring, is a cycle, and another is an open chain. Okay, then it is called ring chain isomerism. See this and CH3CH. This is our pair number 1, this is our pair number 2. Okay, so see, basically they are having different functional group. This is an alkane, cycloalkane. This is an alkene. This is cyclic ether. This is aldehyde. So they are different functional groups. So ring chain isomerism is basically a type of functional isomerism only, but sometimes in certain books it might be referred as different isomerism. If it is a single correct question and both functional and ring chain are there, it would be very difficult to suggest which one you should take as a final answer. In a multi-correct, you have to go for both. That is very clear. But in a single correct, I would always prefer a functional isomerism word over ring chain. But this entirely depends if both options are given and it is a single correct question, then it entirely depends on the jurisdiction of the paper setter, that what exactly he is thinking of. Otherwise, only in multi-correct we should give both the options. Otherwise, either ring chain or functional isomerism should be printed for such set of molecules. Okay. Now, there could be enormous number of examples for functional isomerism, but I am trying to limit myself to the particular exceptions or particular important examples that I consider you need to know are these 4. Okay, we can enlist like for almost 15 minutes only examples of functional isomerism, but where you can make error is these 4, that aldehyde ketone, okay, alcohol phenol, different degrees of amines, and ring chain. These 4 I find more important as a student. Moving to positional isomerism. For positional isomerism, again, our step number 1 is give IUPAC name. That is why IUPAC nomenclature may not be directly asked, but indirectly it influences your marks. It indirectly influences your overall performance. You need to know how to assign IUPAC name to conclude other parts of chemistry. So here, coming back to positional, we'll assign IUPAC name. Step number 2, you will check that the functional group in the 2 molecules is same. Step number 3, you will check that the chain root word of the parent chain or of the substituent is maintained same. Okay, so you have to check the position. You have to check the functional group. Then you have to check the root word of side chain and the parent chain. If these 2 stages you come across and find that yes, they are all same, the only difference between the 2 IUPAC name is in the change, is in the position of either the functional group or the substituent, then you will say, okay, they are positional isomers of each other. Correct? For example, here you will call it as 1 butane all. whereas here you will call it as 2-butanol. So they are both butanol. The only difference is in the position of OH group. So they are called positional isomers of each other. Coming back to this, longest parent chain is taken. Position 2 is having N-methyl. Here longest parent chain is taken. And position 1 is having N-methyl. So see, the only difference in the two names will be the relative position of N-methyl. This one will be called N-methyl butane and this one 2N-methyl butane. So only difference is position. So they are also positional isomers. Now in the above two examples, we have seen that there is a difference in position of functional groups. In example number 3, we are observing that there is a change or there is a difference in position of substituent. Let's see how. First, second, third, fourth, and 5. So this will be named as 2-methyl pentanoic acid. 1, 2, 3, 4, 5. And this will be named as 3-methyl pentanoic acid. So one molecule is 2-methyl pentanoic acid, other is 3-methyl pentanoic acid. The overall difference in the two molecules is only the difference in position of the methyl substituent. So they are positional isomers of each other. Okay, moving ahead, similarly, if you'll see this set, if you go by common nomenclature, we will call it orthoxylenol, metaxylenol, and paraxylenol. Or you can call it simply as 2-methylphenol, 3-methylphenol, 4-methylphenol. So the difference in these three is only the relative position of CH3 and OH. So again, they are called positional isomers of each other. Okay, is that clear? These three are basic. Let's move to metamerism. Metamerism is a characteristic for such functional groups which are bivalent or trivalent in nature, or just bivalent or trivalent functional group we'll write. Now, as far as trivalent is considered, we only have 3 degree amine. Bivalent is 90, I would say 97% cases are of bivalent. See ether, bivalent. Amines 2 degree, bivalent. Ketone, bivalent. Ester, if I could include, surely I can. C2H5CO OCH3 and CH3CO OC2H5, and you can see that the functional group is bivalent. So it is a characteristic of bivalent functional groups. Okay, the functional group is intermittent, is in between the long carbon chains. Correct? So, and the only criteria we need is a difference in alkyl sites. Difference in alkyl sites on the two sides of this bivalent atom. Okay, or even in either one side. Okay, see for example, CH3C3H7, total carbons are 4, and C2H5O, C2H5, those are total 4 only. They are isomers, but the two sides of oxygen here are having 2 and 2 carbon, here having 1 and 3 carbon distribution. But while doing this, while suggesting this, you need to be always keep your one eye on the fact that the functional group of the two molecules should remain same. It should never change in the process. Okay, otherwise you just hypothetically I'm talking, you create a condition, the carbon count here is 0 and here it is 4. So if it is 0, it will become alcohol, which is definitely not a metamerism. It will go into the category of functional isomerism. So while doing this whole thing, that the two sides, the carbon count is being changed or not. Okay, you continuously have to see that yes, the functional group in the given pair of molecules is same or not. Once you could maintain all these facts, then it is okay, we can proceed. Okay, so see amines, 2-degree amines, same similar example. In a 3-degree amine, of course, there are more choices. So C3, 1 and 4, 2, 2 and 1. So different type of distribution, 3, 1, 1 to 2, 2, 1. Okay, then it is metamerism. This ketone is a special stream, special type, which is based on more on I would say, derived nomenclature rather than IUPAC nomenclature. Okay, two sides. This could be a positional isomer pair, and this in fact is a positional isomer pair. This is 2-pentanone, this is 3-pentanone. Okay, 2-pentanone and 3-pentanone, but they are also, by the derived nomenclature, referred as metamerism. This is called diethyl, okay, diethyl ketone, propyl methyl ketone. Sorry, alphabetical, so methyl propyl ketone. So that is why they are assigned this. But again, in a single correct, prefer position as it is based on IUPAC nomenclature. Otherwise, in multi-correct, go for both. Similar to this, we have a distribution. Yeah, this is important because here it is not just the count. If I say this is my functional group, then here there were 2, here 1. You will say, okay, here 1, here 2. So basically the count distribution is same. But the functional group is not symmetrical like the others that we have seen above. So even if in an unsymmetrical bivalent functional group, you exchange the alkyls from one end to another, then also it is called metamerism. Okay, though the count distribution seems to be same, but with which it is attached, it will change their IUPAC names. This is methyl propanoate, this is ethyl ethanoate, and they are metamers of each other. Okay, Tautomerism. Tautomerism is a particular, very specific type of isomerism. Okay, and the word is when two functional isomers are in state of dynamic equilibrium in gas or liquid phase, then it is called tautomerism, and the pair of compounds are called tautomers. Okay, this itself is a very long and a separate topic, but just to summarize as per J syllabus, I would like you to pay attention to this general system of tautomerism. A double bond B, single bond C. C here is not carbon, just a variable atom I want to take, and is connected to H, and then AC connected H, B double bond C. Okay, so there is a shuffling, there is a shuttling of this pi bond and H. If you'll see this pi bond and this H, if this goes here, it comes here. If this goes here, then the bond comes here. So there is a continuous exchange, relative position 1 and 3rd atoms of the hydrogen atom and the pi bond. That is the general criteria we need to check for a compound to exhibit tautomerism. If a compound has this type of system, then yes, it can exhibit tautomerism. Okay, see here, keto, enol. So this is called keto enol tautomerism. This one is called nitro acai tautomerism because they are named on the basis of the functional groups they are having. This is a nitro functional group. This is an acai functional group. This is an amide functional group. This is imidol functional group. Amide imidol tautomerism. Okay, based on the name of the functional groups which are in state of dynamic equilibrium with each other, the tautomerism is named for keto enol, nitroacai, amide imidol, okay, and so on. But these three are relatively more frequent as per our syllabus. So that is why we are more targeting on these three types. Okay. Now, after completing structural, let me tell you one approach to the question, one question I would like to solve. Always in the question, first pay attention. Find total number of structural isomers, very clearly indicated. We need not to bother at all. Okay, we need not to bother at all about the stereoisomers if possible for this particular type of compound. So we'll just not think about that. We are simply asked find total number of structural isomers of C3H6O. So step one you do is you find the degree of unsaturation. I have already done because we have discussed this in our previous lectures. Okay, degree of unsaturation. This is the formula. We have done it last week. Putting all the values required, I'll find that, okay, the degree of unsaturation for C3H6 is O. So now I'm left with this understanding that this molecule will have either it should have one cycle or it should have one pi bond. Degree of unsaturation is 1. Taking this into consideration, you start drawing the structures. So CH3, CH2, CHO. And yes, you have to include the tautomers as the type of isomers. You cannot exclude them. It is a type of structural isomer for a particular molecule. Okay. CH2 double bond CH single bond CH2 OH. CH3 CO CH3. The tautomer will be CH2 double bond C OH single bond CH3. Correct? So I found 5 in aldehyde ketone. Then I move to ether category. CH2 double bond CH single bond OCH3. Now I'm moving to cycle. Okay. I can have, I think, one more. Please check this. Correct? So total number of isomers that I have got is 9. See, the formula was so small, C3H6O, and I got 9 structural isomers. And we are not at all bothered at this moment about any stereoisomerism. Otherwise, it might be a possibility that we would have a greater number here. Okay, let me tell you a fact that the number of positional constitutional isomers increases greatly with the number of available atoms. You must have felt now. Okay, if you go for butane, there are only two butanes, two structural isomers of butanes, N-butane and isobutane. If you go to pentane, you have 3. Okay, you have 3 possibilities. Let me tell you: N-pentane, 2-methylbutane, and neopentane. Correct? If you go to C8H18, that is octane, you will have 18 possibilities of different structural isomers. See how it is moving. In the same series, you'll be amazed, you'll be surprised to see that if you have a 20 carbon 42 hydrogens, that is C20 H42, the number of constitutional isomers will be somewhere in the range of 3,66,319. Can you imagine that number of isomers? And this is why the organic chemistry is so vast and beautiful. Just with a mere combination of 20 carbons, 42 hydrogens, we are not taking any heteroatom. Then also we are having 3,66,319 structural isomers, not even stereos. That is why it is so vast. Okay, so more the number of carbons, more will be the number of isomers. Normally, if you observe the IIT questions, they limit themselves to somewhere like 5 or 6 carbon maximum. I have seen they are not asking more than that, 5 or 6 carbon, when they are asking about open chains. Okay, in case of benzene, yes, it could be more. But if they are asking about simple aliphatic chemistry, then they are limiting themselves to 5 and 6, because they know otherwise the answers will become too lengthy. Calculations and total thing will become too lengthy. Let me give you one homework question. Please attempt by yourself when you revise today's lecture. Okay, so find total number of cyclic structural isomers of formula C6H12. Always in isomers question, pay attention to the language. It is clearly indicated you have to work only at the cyclic structures and structural isomers. You don't have to go for the stereo, you don't have to go for the open chain. It is a trial question for you. Let me write answers here in the corner. It is 12. When you'll solve it, you'll get 12. Okay, so you solve and then tell. So that concludes our structural isomerism totally. Okay, let me go back to the classification we had. So in this isomer category, we have completed this side of our flow chart. That is the constitutional isomers, chain, functional, position, meta, and tata. Now we are moving to stereoisomers. Stereoisomers are those in which the basic link of atoms, the sequence of atoms, the number and the type of atoms are exactly same, but there is some difference in their relative arrangement around the space relative to each other. Otherwise, it is just impossible to find out what is the difference in the two. Okay, so it is very close call. Otherwise, if you don't have a good 3D view, you may get puzzled that what is the difference. They are identical. Okay, so out of these, first we are dealing with conformational isomers. They are also called rotamers. Okay, because they are observed, they are found in atoms which have a single bond. As the single bond can rotate, as the single bond can rotate, as a result of that rotation, there are so many temporary molecular shapes which are created, which are generated. Okay, as a result of this rotation, then they are called conformations of the molecule. Those temporary molecular shapes that results from such a rotation are called conformations of the molecule. And each possible structure is called a conformer. The structure is called a conformer. Okay, and the phenomenon is conformational isomerism. Okay, different possible results, temporary structures, they all together are called conformations. Okay? When we analyze the energy changes that occur as a molecule undergoes rotation about single bond, it is called conformational analysis. Okay, to represent this on paper, we usually have two choices of representation. We have two representations to study conformations. First is Newman, second is Sohars. These two are commonly used. Yes, you can use wedge dash also and all those, that is okay. But the primary two important. And if you see JE, I have seen that they are using this relatively slightly more. You can use Sohars, no issues. So let us exemplify our point first with ethane. Okay, let us exemplify first with ethane. Let me take a risk. I would like to um, unshare the screen to show certain models to you and then come back on the screen to show it back. I don't know, but I'll take that risk today. I hope you can see me now. Now, see, when I have ethane as a molecule, okay, when I have ethane as a molecule, I hope you can see this structure, ethane. Okay, polyenstic structure. So what I was telling in confirmation that about this single bond, my molecule can rotate. You can ask, it can rotate about this bond also. Yes, it can, but about this bond there would not be any different structural arrangements, so I'm not bothered about it, but it is possible. I'm bothered about this because when I have rotation about this single bond, if I rotate this towards you, towards the screen, the arrangement that I want to show you now exactly is a fully eclipsed. Behind this carbon, the behind carbon is eclipsed, is not visible. Similarly, should be the condition of these hydrogens. Okay, but they are there. If I rotate about this single bond, you can see an arrangement. Okay, you can see an arrangement in which between the V of this front hydrogen, this back hydrogen can be seen. And similar will be the case with all other positions. See this. This is the staggered conformation. But when we do this rotation, there are so many enormous possible arrangements. They are all different arrangements. So that is why conformation is there. Is it okay how the conformation is around? It is about a single bond due to rotation. Now, if I change these molecules, because when I'll start butane, I would not like to take the risk again coming back to camera. So here, assume these two greens as methyls. Okay. So there is carbon and having three hydrogens, and then again carbon and three hydrogens. You can feel the two hydrogens here will be having steric repulsions with one another. Similarly, if I'll rotate it towards you, you will again have the same thing, the fully eclipsed, the partially eclipsed, okay, and the different NT and gouge conformations. So this is how the overall conformation is there. We are talking again, limiting ourselves to JE syllabus. So ethane and butane, otherwise we might have to go a much way ahead towards the cyclic and the different type of molecules with lone pairs and all that. But let us first go to our syllabus concerned time. So this is how it appears in 3D. This is how it appears in 3D, but how it appears on paper. Okay, on paper you will see these two arrangements. So this is staggered, this is staggered, this is eclipsed. If you could relate to what I just shown you, or when I close the lecture, please do the scroll reverse and forward thing and match. Here it is front hydrogen is totally eclipsed from backside. So this is eclipsed, this is staggered, this is staggered. When it is eclipsed, then definitely the hydrogen will have much less distance between the two, and as a result there will be steric collisions between these two molecules. Okay, there will be steric collisions between these two molecules. This will make this structure unstable. Okay, whenever two atoms come close, there is a state of repulsion. Certainly, the best thing, minimum repulsion, is if I place them to infinite distance. But that is a very theoretical point of view. Then I cannot form a molecule. To form a molecule, I need to bring them at a certain safe distance where the repulsions are minimum possible. Under our limited possibility that I cannot place these atoms to infinite distance, my choices are, okay, my choices are two in case of ethane, eclipsed and staggered. All other arrangements will fall on this slope and they are together called skew conformations. This graph is, if I start taking this as a zero dihedral angle, then as I move 1 degree, 2 degree, 3 degree, 4 degree, say 60 degrees, and then again coming to 120 degree and so on, I'll have a repetitive graph. And here is the change in potential energy of the different conformers. Correct? Now see, here I have written a word torsional barrier. What is the torsional barrier? Torsional barrier is the energy difference between the most stable and the other conformer that we are seeing. Okay, torsional barrier is the energy difference between the most stable and the other conformers. So, in case of ethane, that value is 12 kilojoules per mole. And please note the word 12 kilojoules per mole. What is mole? Mole is an Avogadro number of molecules, 6.02 into 10 to the power 23 molecules. Just imagine 12 kilojoule is required by such a vast number of molecules. So, no need to tell me for one molecule you can feel how less, how small value of energy is required. Okay, so if we require this, I would say negligible energy is required for our molecule to rotate from one conformation to another. Okay, and that is why this is a spontaneous behavior of any molecule. It always keeps on moving from one to another arrangements spontaneously at all conditions, at all room temperatures. Yes, there could be difference, there could be effect of temperature, but it is never going to stop. It is never going to be no equilibrium is stopped, is seized. It is never that in case of conformations. I use the word dihedral angle few minutes ago. So let me exemplify what is dihedral angle. In case of ethane, we had front carbon, if I say, with red, and back carbon, this green, its substance, if I say, is H, H, and H. So, what is dihedral angle? Front carbon H, back carbon H. Okay, back carbon H. So, let me name them C1, H1, C1, C2, H2. Others are there. अभी मेरा उसमें interest नहीं. So, a plane X having H1, C1, C2. Okay, and there is a plane Y having H2, C1, C2. There are two planes. There are two planes. Angle between between plane X and Y is called dihedral angle. Okay, angle between these two is called dihedral angle. Is that okay? So see, I can say in eclipsed conformation. In eclipsed conformation, which is here, if I draw these as a plane, this is my x. In this given structure, तो y भी इसी में दिख रहा है ना? Y is overlapping. I would say I need to use some other specific color to differentiate. If I do this, they are overlapping plane. So in eclipse conformation, dihedral angle is 0. Okay, but if I go to staggered, if I go to staggered H1C, this is in H2. Okay, let me draw it fast for you. This is my plane X, and this is my plane Y, and the angle between these two is 60 degree. This, so in staggered, dihedral angle is 60 degree. Okay, stability of different conformers, stability of different conformers of C2H6. सबसे ज़्यादा stable is staggered, then all others skew, and then it comes the eclipsed. Eclipsed is the most unstable. Okay, eclipsed is the most unstable conformer out of the all. Is that okay? Eclipsed is the most unstable. So let's move further to butane. To save time, I have already drawn the structures of the different conformers of butane. In case of butane, we have CH3, CH2, CH2, CH3. 1, 2, 3, 4. So what we are studying is about rotation along C2, C3 carbon. Okay, we are studying our conformation of butane along C2, C3 carbon. So along C2, C3, there are 6 possible arrangements. And don't get confused anywhere that this gouge and this gouge are same. They are mirror images of each other. They are not same. So total there are 6 arrangements. Okay, if I compare their relative stabilities, if I compare their relative stabilities, then NT is the most stable one. Those which are fully eclipsed. Okay, this is fully eclipsed. Where is other fully eclipsed? No. These two are partially eclipsed. This is also partially eclipsed. When H and methyl are coming in front of each other, then it is called partially eclipsed. Okay, when H and methyl are coming, then it is partially eclipsed. When it is CH3 is coming in front, then it is fully eclipsed. Fully eclipsed is the most unstable. Partially eclipsed, then is the couch, and then the NT. This is the order of this stability. So see, most stable is NT. So to find the torsional barrier, that is, torsional barrier indicates how unstable the given conformer is with respect to the most stable. Okay, now let us see. If I take NT as my reference scale 0, I cannot say that potential energy of NT is 0, so I cannot draw this scale here. It also has some potential energy, but for a reference purpose, for torsional barrier, we take it as 0. Otherwise, it is certainly not 0. Okay, this NT, another is here. So when you move NT to partially eclipsed, you need to give 16 kilojoules per mole to the molecule. I have tried to maintain in kilocalories also parallelly. Okay, so just for your idea, just for your vision that what the values are. So 16 kilojoules per mole I need to give the molecule so that it can overcome the repulsion and can somehow rotate to this partially eclipsed. When this partially eclipsed move to next state, that is gauge, then it releases some energy, though with comparison to NT, it is still having 3.8 kilojoules per mole higher energy. So more stable is NT, then it is gauge. Okay, then it is fully eclipsed, which is maximum energy, see, 19 kilojoules per mole, and then similarly it moves on. Okay, so if I say that our molecule butane, if I could say that the molecule butane is CH2X CH2Y type. Okay, CH2X CH2Y type. In case of butane, the X and Y were methyls. But there is always a possibility that there could be some different groups. है ना? So what? X and methyl. So let me make some note. Point number one, if X and Y are alkyls or non-polar groups, then anti-conformer is the most stable one. Okay, you can take example of N-butane. If X and Y, if X and Y are same charged groups, then again, then anti-conformer is most stable. Okay, बोले ये भी हो सकता है. Is this possible? Yes, you can have CH2CO minus CH2CO minus. You can have CH2NR3 plus CH2NR3 plus. For these, we need to have NT. If X and Y are oppositely charged or are capable of H bonding with each other. Then gauge conformer is the most stable one. Okay? If X and Y are oppositely charged or are capable of intramolecular edge bonding with each other. So again, moving to example, this is very important. Huh? Please pay attention to this. On this point, JE has asked the questions. CH2OH, CH2OH. You can have CH2, NH2, CH2, COOH. You can have zwitterion of glycine, NH3 plus CH2CO minus. Okay, you can have CH2OH, CH2F, and I would say etc. But please record this in your brains very well. This is important. That if there is a possibility of intramolecular edge bonding, or if there is a possibility of opposite charge attraction, then for the similar arrangement, gauge conformers will become most stable one. No more NT is the stable most. Okay, so that brings us to the closure of conformational isomerism. Let us move to geometrical isomerism. Okay, and please, one thing I would like to add here that I am teaching organic chemistry. You are in a mind frame, you are in a frame of vision that, oh, we are studying only organic molecules. So conformation or any type of isomerism that we have studied till now is a property of organic molecules. So let me make it clear that no, not at all. In any of the definitions that we might have studied in case of conformation or the word isomerism, we never ever said that there should be presence of X number of carbon atoms. Okay, so what I'm saying, why I'm saying, yes, we have exemplified due to our limited time organic molecules, but why not? H2O2 also has conformations, and H2OH also has conformations. Hydrazine has conformations. Correct? I would write etc. So it is a property of organic as well as inorganic molecules. Because conformation has no statement that it is related to carbon. It says different arrangements about a rotation of a bond. Okay? You can have it even in the cyclic systems. Similarly, coming to geometrical isomers, it is observed in both organic as well as inorganic molecules. Where in inorganic molecules, why not? You can have this N double bond N type linkages, right? You can have diamide. Diamide has geometrical isomerism. In case of coordination complexes, there is geometrical isomerism. So many places we have geometrical isomerism. Now, what is geometrical isomerism? What should we check for geometrical isomerism? Okay, so first thing you need to check is there should be restricted rotation about a bond or group of bonds. Point number one, there should be restricted rotation, either a bond or a group of bond. A bond, then I can say a double bond. A group of bond, then I will say cyclic systems. Cyclic systems. Okay, coordination complexes. You cannot specify which bond alone is responsible for restricted rotation. It could be set of bonds involved. Okay, and about this restricted rotation, there should be two different three-dimensional arrangements possible. Okay, there should be two different. These two structures cannot interconvert from one to another at normal room temperatures. They need assistance of high temperatures, high pressure, some conditions where we need breakage of bonds, we need reformation of bonds. So in case of alkenes, if I say C double bond C A, B, C, D. Yes, I can have A, D, B, C. This to this is geometrical isomerism. Let me draw one more. If I draw A, C, B, D, okay, then this is not GI. This is not GI. If you see, I think this is positional isomerism. I have changed the relative position of B and C. Whereas here, if you give IUPAC, the one position 1 has A and B, position 2 has D and C. Same is here. Correct? So always we need to check that the particular arrangement should not change the relative positions of the group. 3D position is change is okay. Right? So example, very basic example that you have been studying all along is cis 2-butene and trans 2-butene. Okay, this is a very common example in case of alkenes. Similarly, you can have a geometrical isomerism in oximes R1, R2, OH, lone pair, and R2, R1, OH, and lone pair. And lone pair. So these are two different geometrical isomers. Okay, so these are two different geometrical isomers and so on. ठीक, so oximes हो सकता है in case of cycloalkanes you can have. For example, if you have A, A, B, B, then the other arrangement could be A, A, B, and B. Okay, you cannot rotate about this bond and get conversion to each other. You need to break the bond. That is the only way. In case of cycloalkadines, yes, these are the cumulative dienes we have studied. So when there is planar arrangement, A, B, A, same plane. Okay, when there is, just to avoid this A, B thing, I will rename this with something else. Let me write it X, Y, X, Y. So when it is planar, then you can have another arrangement which is this. These two are GI of each other. Okay, geometrical isomers have, and so on. There are so many possibilities. Geometrical isomers have different physical and chemical properties. Okay, they have different dipole moment. In case of, say, 2-butene, in case of 2-butene, I will say cis versus trans. If I compare, then dipole moment of cis is greater than trans. But there is no fixed rule regarding this. There always has to be a clear vision that what molecules are attached. For example, here, if I say cis and trans, then this is our trans, this is our cis, mu of trans is greater than cis. So there is no fixed rule, it depends on the groups present. But once you analyze the dipole moment order is what, then I can say boiling point will be directly responsible on dipole moment values. Whichever isomer has higher dipole moment will have higher boiling point. Water solubility directly proportional to dipole moment. Whichever isomer higher dipole moment will have higher water solubility as like dissolves like. Oh, but melting point, nothing to do with dipole moment. Nothing to do with dipole moment. Always trans has higher melting point than cis. And the reason is compact packing. Compact packing. Due to compact packing, always trans isomers will have higher dipole moment than uh, always trans isomers will have higher melting point than other ones. Okay, I'm just scrolling down this number of calculation of number of geometrical isomers, but we'll definitely discuss it in the coming sessions. These are the formulas. Okay, n is the number of sites which can have geometrical isomers. Okay, just to show you the geometrical isomer of C-cyclic systems. You can see these green. I cannot rotate it and change it. For change, I need to break these bonds. Now only I can bring to a different relative arrangement about the restricted rotation, the two greens. That is why cycloalkanes, if suitably substituted, can have geometrical isomerism. See alkenes. In case of alkenes, I am using these purple, purple, okay. So these are oppositely placed about this double bond. And if I want to bring them to cis geometry, I need to break these bonds like this. So only breakage of bond can bring them from one to another. So this is the difference from conformation. Conformation, spontaneous. They cannot be. Right? So here we conclude our lecture on structural and geometrical isomers. Tomorrow we'll concentrate on optical isomers. Please go through the lecture, revise your notes, and do as much numericals as possible on all of these concepts.